Hi everyone, welcome. Thank you for coming to see us today. My name's Oliver Sanders, Commercial Director for Data Centres UK&I Ireland for Carrier QuantumLeap Data Centre Solutions. We spent the last year talking about AI. We talk about the generative models, the magic it creates, the speed. But today I don't really want to talk about the magic. I want to talk about the cost of that magic. Because when you really take away the software and the hype, AI really is just heat. It's the conversion of electricity into calculation and with heat as the byproduct. As we move into this new era, the rules of how we manage this is fundamentally changing. Today, I want to take you back to those first principles. So let's ask ourselves, why are we densifying? Why are we packing 100 kilowatts plus into a rack? It's not just to save on space and rent. We do it because of speed. We do it to make calculations faster. We need to move the data faster. To get more performance the AI demands, we have to shrink the physical distance in between the chips. But when you shrink the volume, you're concentrating that energy. And we are now putting a massive amount of energy into a tiny box. And physics dictates that that heat must go somewhere. The problem is, our industry tends to slice this challenge into pieces. AI buys the servers. Contractors and DC builders buy the chillers. Mechanical engineers and consultants size the heat loads. But heat doesn't really care about your job titles. Heat flows in a chain. It goes from the chip to the rack, to the room, to the loop, and then finally to the outside world. But every time you hand that heat off, you introduce a penalty, a temperature difference, a delta T. And if you only look at your slice, you may look at the inefficiencies compounding the whole system. If you remember one thing from today, remember this balance. To move heat, you need flow and a temperature difference. But as density goes up, if you try and pump more water and move more air, you'll hit a wall. Higher flow means massive pressure drops. Massive pressure drops mean massive pumps and enormous pipes. Suddenly, your CapEx will explode. We have to stop designing from the chip forward. We need to start building it. We need to stop designing from the chip forward to hope that our DC can handle it, our system can handle it. We need to start designing from the destination backward. Which brings us on to phase 2, the 4 destinations. If you walk the data center world floor today, you'll see hundreds of companies selling thousands and thousands of different cooling products. But if you look at the physics, there is only 4 destinations and 4 possible routes where that heat can go. And we like to call these the 4 destinations. That's it. There's no magical 5th dimension that we're all hoping for. You are either putting that heat into the air, into evaporation, into a heating grid, or into a large body of water. So let's take option 1, dry cooling. We look at the air as an infinite sink. And globally, it is. But guess what? Air's a pretty bad conductor of heat. To cool a 500 megawatt data center or AI factory, you can't just turn the fans up. You can't just blow air at 200, 250 miles an hour and hope that we can get it out and have those PUEs that you actually all desire. We need to make the building bigger, much bigger. And if you stick with that, eventually you'll hit a wall. You'll hit that physical wall. Option 2, evaporation. We all know water is a very sensitive topic, and if we don't want to use water, we really don't want to, and we don't have to. But evaporation is thermodynamic magic. It's an order of magnitude more efficient at rejecting heat than air. As densities rise, if they triple even, physics may actually put you here. Okay, so it's just worth thinking about that. You simply can't get heat out fast enough than the phase change of water. Option 3 is heat reuse. It's our favorite. We take that heated water, 50, 60 degree water, and we go and utilize it to heat a hot water and start looking at residential applications and domestic water. Technologically, this is fairly easy. We have the heat exchangers. We have the most efficient products to be able to create this and boost that water up even if we need to. The problem is geography. You need a population. You need a population to accept the heat. You need someone to own that heat. You can't do it in the middle of the desert, obviously, but in a large condensed city area, you can turn that waste product, that waste heat, into a revenue stream. Lastly, water. A large body of water, the river, the lakes, the sea. This is the ultimate thermal mass. The river or the lake or the sea, it doesn't care about your 100 kilowatt rack. It will eat it up in seconds. The point is this. Before you buy a single GPU, you need to know which of these 4 destinations you are using, because that decision dictates everything else inside the building. Which brings us on to phase 3, which I'm calling the hybrid reality. So we know, so how do we actually cross this thermal wall without going bankrupt? How do we bridge the gap between the legacy air-cooled data center and the liquid cooling future? We've got a bridge technology. We're using a hybrid. So we know where the heat goes, but how do we capture it? Everyone is talking about direct-to-chip cooling, direct-to-chip liquid cooling, DLC. But here's a reality check. Pure liquid cooling is a myth. Might have some raised eyebrows here. Even in a rack full of liquid-cooled GPUs, you still have power supplies, you still have memory, you still have networking gear, all that is air-cooled. And as we densify, we increase the load, we increase the capabilities of what we actually need, and we increase the capacity. You might capture 80% in liquid, but that remaining 10-20%, remember, is still hot air. You can't just delete the air handling unit and the mechanical elements into this equation. Which brings us on to the hybrid paradox. Okay? Stay with me. Stay with me. I like to compare the modern day data center to a plug-in hybrid car. Let's say my BMW. Other vehicle manufacturers are obviously available. If you look at the physics, and let's be honest, a hybrid car is technically a very bad car. Once again, stay with me. It's heavy because it's dragging around a petrol engine and a massive battery. It's not optimized for electric efficiency, and it gets worse petrol mileage on its own because of the weight. We're doing the same thing. We're building hybrid halls. We're buying massive chillers for the air side and massive CDUs for the liquid side, increasing or doubling our infrastructure. So, why do we build these expensive, heavy hybrids? For the same reason you build the car or you buy the car: security. You buy the hybrid so you don't have range anxiety, and you can drive on electricity in the city or petrol on the motorway. In the data center, the hybrid lets you run legacy workloads and high-density AI in the same room, it's an expensive bridge, and you're likely paying for 100% air capacity and 80% liquid cooling capacity at the same time. But right now, this is the only vehicle that gets us safely from the past into the future. We've defined the problem. We're facing the thermal wall. We're building complex hybrid bridges to cope with it. So how do we... and now we know the physics dictates there's only 4 ways that we can get this heat out. The temptation now is to go and buy a bigger chiller, a stronger pump, bigger fans. But that's legacy thinking, okay? That's trying to smash through the wall with brute force. To handle the gigawatt era, we don't just need incremental steps. We need a fundamental shift in how we connect the chip to the atmosphere. We need a quantum leap. Oh, by the way, I just got that one past marketing. Our units, if you know, it's quite good in a way, if our units did get delivered like that, they stay in one piece, which is great. At Carrier, QuantumLeap isn't just a product brochure, it's a framework for integration. It's how we stop the slicing problem. It's a methodology that takes the heat from the AI chip, manages the hybrid cooling loop, and delivers it efficiently to whichever of the 4 destinations you've chosen, whether that's the air, the river, the cooling tower, or a district heating grid. Here is the takeaway. Density, obviously, is non-negotiable. The hybrid reality is expensive, but necessary. And the laws of physics are certainly not changing. The biggest risk to your project isn't buying the wrong chiller or the wrong CDU. The risk is the gap in between them. The risk is failing to connect the physics to the chip to the physics of the destination. We are entering an era where the data center is no longer just a building with air conditioning. It's a complex thermal power plant with the opportunity to do so much more. The challenge to you today is, before you buy any components, stop looking at the chiller in isolation from the rack. Start looking at designing the entire thermal life cycle. So thank you. If you're ready to move on beyond this hybrid paradox and engineer a solution that can sustainably deliver and scale, come and find us on stand D70. Check your geography, pick your destination, and we can look at that leap together. Thank you very much.
Well done.